Okay, quiz 15.3 is just a whole heap of practice with using ice tables in different situations. So let's dive right in. This reaction has carbon solid. Oh my goodness. Sorry, I'm breathing in chalk dust. Plus water vapor in equilibrium with carbon monoxide and hydrogen gas. And we'll go ahead and set up our ice table, at least the structure of it. We're going to have concentrations of hydrogen and carbon monoxide and water vapor. Carbon is a solid, so it doesn't appear in the equilibrium expression. And Kc, as you see down there, is given as 5.63 times 10 to the negative fourth. And that is going to equal concentration of carbon monoxide, concentration of H2 over the concentration of H2O. I'm actually going to just make the quiz disappear for a moment so we have the full board to work with. Now I've got everything set up, and this kind of a setup should hopefully become very familiar to you. It's getting everything in place to begin to tackle equilibrium type problems. So I'll pull this up again real quick just so we can see the concentrations. So give the equilibrium concentrations of all species if we have excess carbon solid, and that is important. We need to, even though it doesn't appear in the equilibrium expression, we do need to have carbon present and in sufficient quantity for the reaction to reach equilibrium. So we'll have an excess amount of that carbon solid, and then we'll have water vapor at 0.250 molar. And that's it. So we want to figure out the equilibrium concentrations for everything else. We'll start with 0 amounts of products. Here we have negative x, plus x, plus x. And so we're left with x, x, and 0.25 minus x. The equilibrium amounts are the initial amounts plus the changes. And the changes come from our stoichiometric coefficients. Now we can go ahead and put those values into our equilibrium expression right here. That carbon monoxide concentration times the hydrogen gas concentration, that's going to be x squared. And then the water concentration is 0.25 minus x. Okay, now let's see if we can make this equation a lot simpler. I don't want to do the quadratic formula. I hope we can avoid doing that. And so if x is much less than 0.25, then 0.25 minus x is pretty darn close to 0.25 itself. And we're going to assume that it's close enough that we can just ignore the x right here. This x, we're just going to ignore it. Or, since this is a chalkboard, I can easily just erase it. We've gotten rid of that minus x. And now it's a lot easier to solve for the concentration. X squared is going to equal 5.63 times 10 to the negative fourth times 0.25. And if we just take the square root, oops, there we are, of both sides, then we can get x is equal to the square root of the product of those two numbers, and we end up with x is equal to 0.0119. Now, Is 0.0119 much less than 0.25? Well, we have a threshold. I'm going to take 0.0119 divided by 0.25 times 100%. That's going to tell me how big this number is as a percentage of the number I subtracted it from. And it looks like it's going to be 4.76%. As long as this number is 5% or smaller, then that means our assumption was good enough that we can move forward and we don't have to do the quadratic formula. In this case, it was a very close call, but thankfully we can go ahead and use that number moving forward. We don't need to do the quadratic formula. And so if x is equal to 0.00199, then our equilibrium concentration of hydrogen is 0.0119 molar. And our equilibrium concentration of carbon monoxide is 0.0119 molar. And 0.25 minus 0.0119 is going to give us 0.238 molar. Those are the equilibrium concentrations, and that's it for question 1. It goes really smoothly. As long as that number is less than 5%, they're really not that bad. Now, if we had to do the quadratic equation, then it would just be a whole heap of algebra. We would need to keep this minus x and solve for a form of this equation, ax squared plus bx plus c equals 0, and apply the quadratic formula. Thankfully, we didn't have to. Okay, so let's look at the next question. We have PCl5 and this is a gas in equilibrium with PCl3, which is a gas, plus chlorine gas. We'll put up our ice table. And our equilibrium expression, we know that the Kc is equal to 0.0160, and that's going to equal the concentration of PCl3 times the concentration of chlorine gas over the concentration of PCl5. And this one is a little bit interesting. So we have an amount of pure PCl5 placed in an empty chamber. And that's all we're given in terms of initial conditions. So you can already tell this one's going to be a little bit different. Let's read the whole thing and then talk strategy for how to solve this. After equilibrium is reached, then the product concentrations are measured as PCl3 is equal to PCl2 is equal to 0.0134 molar. So what do we know? This is the only number that we really have, 0.0134 molar and 0.0134 molar. And we also know that it was an empty chamber, and so we have zeros right there. Now, how can we use this to solve what we really want is to know the initial and equilibrium amounts for PCl5. Well, let's think about how this would usually look. We'd have, negative x, and plus x. That much we know. And if 0 plus x equals 0.0134 molar, well, then we know the value of x. X must be 0.0134. 0.0134. And that means that this is a negative 0.0134. And we can call our initial amount of PCl5, we can call it y. In the answer key I called it x, but just to distinguish it from what I usually use for change, we'll give it a different name. We'll call it y. And here we have y minus 0.0134. Well, now we can solve this equilibrium expression just like before. We have values that we can plug in here. So we can say 0.0134 times 0.0134 over y minus 0.0134. And we just have the one unknown. So what we'll go ahead and do is perform that square operation on the top, and then move this over to the left side and distribute the 0.016. And so what you end up with is 0.0160 times y minus 2.4 times 10 to the negative fourth. That's 0.016 times 0.0134. And that is equal to 1.796 times 10 to the negative fourth. And that looks like a 3 on the screen. But it really was a 4, it was just a funny looking 4. Okay, maybe that's a little better. And we can add the 0.214 times 10 to the negative fourth to both sides, divide by 0.016. Anyway, in the end we get y is equal to 0.0246 molar. And so here we can now give our initial concentration 0.0246 molar. And then what is 0.0246 minus 0.0134? That is 0.0112 molar. That is our equilibrium amount. Okay. One final problem, question 3. So here we have a reaction Cl2 gas plus Br2 gas in equilibrium with 2 BrCl gas. We'll draw the ice table. And we know that Kc equal to 7.20, and that's going to equal the BrCl concentration squared over the Cl2 concentration, times the Br2 concentration. We say find the equilibrium concentration if a chamber is charged with 0.5 moles of Br2 and 0.05 moles of BrCl. Now this is one of those cases where we weren't given a volume, and so actually I can't really give you the concentrations. I need to fix the wording of this question. But we can still solve it and find the number of moles. Because our concentration here would be divided by the volume, and that would be squared. And each of these concentrations would be divided by the volume, and that ends up being volume squared. The volumes can cancel out of this formula. And so what you would end up with is n BrCl squared over n Cl2 n Br2. So you can do this trick for Kp values and for Kc values when delta n is equal to 0. Those incidentally are also the cases where Kp equals Kc. And so this trick wouldn't work for everything, and you know, I could go back and rewrite this quiz and fix it, but because it actually is possible to solve for the number of moles, that actually makes this maybe an interesting question, and I'm going to leave it. So those are the moles that we start there, and we have a 0 right here. Now looking at this, if we were to try to calculate Q, because we have some product and we have some reactant present, well, Cl2 is in the denominator and it's actually a 0, so our Q is infinity. It's obviously greater than K, and so we don't have to have any guesswork here. We know we're going to have a minus 2x here, and a plus x here, and a plus x there. In other words, this reaction is going to have to shift toward reactants in order to reach equilibrium because it started with absolutely 0 Cl2. And so we'll end up with 0.05 minus 2x, 0.5 plus x, and x. Okay, so let's go ahead and erase all of this here and just put in numbers. (0.05 minus 2x), that needs to be squared over x times 0.5 plus x. Now, x is going to be smaller than 0.05. At the very least, we know that x will be reasonable to ignore here. And that would make this a little bit easier to solve. But I'm going to go ahead and be ambitious, and I'm going to hope that if 2x is much less than 0.05, then I can ignore this x as well as that x. And that would make solving this really, really easy. And let's just hope we can do that. And so with our assumptions, maybe I should say this is approximately, we would have 0.05 squared, because that x is small enough that we don't see a lot of change here. And we'll divide that by x times 0.5, because that x is small enough that it doesn't change the value here very much. And so we're left with 7.2 is equal to 0.05 squared over x times 0.5. And that's pretty straightforward to solve. Let me get my chalkboard's bottom part back here. Okay, we can solve that and find that x is equal to 6.94 times 10 to the negative fourth. Now, let's make sure that our assumptions work. Basically, I want to say 2x divided by 0.05 times 100% and see how much this quantity is as a percentage of that quantity. And it works out to be 2.8%. And so we're justified in making that simplification. Now, if you're wondering about over here, well, 2x is only 2.8% of 0.05. It's going to be even smaller there. We don't even need to check that. If this assumption is good, then that one is certainly good as well. And so that's low enough that thankfully this very simplified form of the equilibrium expression is valid. And now we can start putting x in here to figure out our equilibrium concentrations. This would be 6.94 times 10 to the negative fourth molar. Now 0.5 minus that is going to be, plus 0.000694 is going to be 0.501 molar. That rounds up just barely. It's going to cause a tiny, tiny change there. And then 0.05 minus 2x is going to give us 0.0486. Oh, and these aren't concentrations, these are just moles. 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 Okay, we could turn these into concentrations if we knew the volume. The question didn't give you a volume, so these are just numbers of moles. And because this one was a little tricky, let's go ahead and go back and try plugging these numbers in to our equilibrium expression and reassure ourselves that, that this is going to work out nicely. Okay, so what do we have? 0.0486 squared divided by 0.501 divided by 6.94 times 10 to the negative fourth. That's going to be 6.79. Oh, hold up. KC should be 7.20. Oh, I've done it again. I do remember this from last year. That 5% rule is designed around the sorts of problems like the first one that we did, where the quantity we subtract from x, or the quantity that we subtract x from, is only raised to the first power. And in this case, what we have is, in this case, what we have is the quantity that we subtract x from is squared. And that's going to make everything a little bit more sensitive to any errors that we may have made. Okay, well, this was not intended, but maybe we can explore another way to solve this that isn't going to require us to use the quadratic formula. Because I hate the quadratic formula. And as long as we've done all of this work, we can actually use this value of x that we've found and refine our simplifications. So these concentrations that we calculated based on this value of x, let's go ahead and put them back into this formula. So remember, this was the concentration of BrCl, and we were going to square it. And we had just left it as 0.05. well, this isn't the right answer, but it's close to the right answer. And so that means this is close to the right answer as well, certainly closer than 0.05. So let's do 0.0486 squared over x times 0.50, and let's do 0.7. We'll carry an extra sig fig there as well. Okay, now if we do that and solve for x in this case, we'll get a new value of x that will hopefully be closer to the true value, and we didn't have to do the quadratic formula. This is what we could call an iterative approach, because we're applying the same formula like a second time, and we're slowly converging on the true answer. This is entirely unplanned, so it's kind of fun. All right, that means that x is going to be 0.0486 squared divided by 0.5007 divided by 7.20. And I get a new value for x, that's 6.55 times 10 to the negative fourth. And if we compare that to our original value, 6.94 times 10 to the negative fourth, we do see some change here. So is that going to be good enough to satisfy our equilibrium expression? Well, let's figure that out as well. So we're going to have 0.000655 is our value for x. Let's calculate now. I'll write them down here. New concentrations. So we'll have 0.05 minus 2 times 0.000655. That's going to be 0.0489, 0.0489 moles. This is our new concentration here. And then this will still round to 501. It will still round up. And this will now be 6.55 times 10 to the negative fourth moles. There we go. And using those new values now, hopefully we'll get something that is going to satisfy the equilibrium expression. So we have 0.0489 squared divided by 0.501 divided by 6.55 times 10 to the negative fourth. And now it's equal to 7.28. Now it's a little bit too high. Last time it was a little bit too low, but this one is much closer. So let's do it one final time. Let's solve for x even newer. So we're going to say that x is equal to the 0.0489 squared divided by 0.5007 divided by 7.20. Now we get an even newer value of x, 6.63 times 10 to the negative fourth. And I'm hopeful that this one will finally get us to satisfy the equilibrium expression. Okay, so we're going to have 0.05 minus 2 times 0.000663296. Actually, let me just grab that output directly. Out 29. And that'll be squared divided by out 29 and divided by 0.5 plus out 29. And we'd better enclose those in parentheses. Oh, we're bouncing around. Now that one is still closer. Well, you can kind of see where this is going. We can set some bounds. We know that our value should be between 6.55 and 6.63. At this point, if you really hated the quadratic formula, you could continue this iterative process, or you could even exhaustively try the 8 numbers that are between those two numbers on the number line and just choose the one that most closely matches the quadratic formula. Most closely matches the equilibrium expression. I'm going to go ahead and just cheat here. Okay, so give me just a moment. Okay. If I'm being perfectly honest, this is how I would solve a problem like this. I would go to Wolfram Alpha, which allows for solving equations, and I'll just do 7.2 is equal to 0.05 minus 2x squared divided by x times 0.5 plus x. That'll solve the quadratic formula for me. Let's see what it tells me for the value of x. Looks like x is 6.57 or 6.58 times 10 to the negative fourth. And so almost right perfectly in between our x new and our x newer values. Okay, bottom line, I didn't want to do the quadratic formula again. I know you don't want to do it, and in the modern day, most of the time, there's some way to avoid doing the quadratic formula. This particular problem satisfied our 5% rule, but because the error that included that 5% was squared, that made our 5% rule be a little bit too generous. We should have been more strict about that. And that's what actually made our first value of x here not work when we tried to plug it back into our equilibrium expression. And that's something that I did not catch when I wrote the paper key. And so that's a little bonus Easter egg that you get watching here on the video. I'm sorry about that, and in future years I'll just I'll change this problem. I'll adjust it to make sure that that's not going to be an issue.